electronics. Today's video is a preparation for Space Application Center Scientist and Technical Assistant exam preparation. And we are going to see the questions from the session Resonance in Series RLC Circuit. So this is a very common topic, and this is a topic which usually examiners prefer to ask questions about. And these questions, at least one question, will be seen in all question papers of any competitive examination of electronics. Okay, so this is a very asked type of question. Okay, so I've done a detailed video on the resonance in series RLC circuit, the theory video I've done, and we are going to see questions which are being asked in the previous year ISRO examinations in this video. Okay, so the first question is this. So if you're not familiar with the theory of series RLC circuit or resonance in series RLC circuit, please do watch that video. I'll share the link in description box. Okay. The first question is, a series RLC circuit resonates at 3 megahertz and has 3 dB bandwidth of 10 kilohertz. The quality factor of the circuit is dash. So what is the quality factor of a series RLC circuit? The quality factor, I've explained about these quality factors and bandwidth and the curve, resonance curve of a series RLC circuit. What is resonance and at resonance, what is the criteria? All these things I've explained in detail in another video. So I'll be sharing that link in description box. So please check out that video to know about the theory of series RLC circuit and resonance in series RLC circuit. Okay. So here we need to find the quality factor Q. So if you see the curve of resonance of a series RLC circuit, the point at which this peak is actually contributed by the maximum value of current. Okay, so where the maximum value of current is happening, that is called the peak. And this, in order to characterize the peak, we use that quality factor. Okay, and the quality factor is represented by, the equation for finding quality factor is F0 by bandwidth. Okay, this is the equation for finding the quality factor of a series RLC circuit. F0 is the resonant frequency of that circuit. So here, if the RLC circuit resonates at 3 megahertz, means that is the resonant frequency, F0. Bandwidth is the bandwidth of this curve. So this curve will be having higher, lower cutoff frequency and upper cutoff frequency. And this region or this contributes the bandwidth of this particular curve or this circuit. So here, both the values are being given in the question. What is F0? F0 is 3 megahertz, that is 3 into 10 raised to 6. By bandwidth is 10 kilohertz, 10 into 10 raised to 3. So the answer will be 300 is the quality factor of this particular circuit. So I am telling it once again, if you want to know about the theory of quality factor, resonance, the criteria, what all things you have to consider in resonance, what are the various features, all these things I have explained in detail in that video. Please do check out that video. Next question. At 3 dB frequencies, I'll remove this to make some space. At 3 dB frequencies, current in the series RLC circuit equal to the current at resonance multiplied by dash. Okay, so if you see the curve, resonance curve of a series RLC circuit, this is the peak value of current. Okay, so this is actually a curve of current. Here you represent angular frequency, or you can represent natural frequency in hertz. This will be current. Okay, this is the peak value of current at resonance. This point we say as resonance, and this frequency we call it as resonant frequency. If it is represented in radians per second, you can represent it as W0 or omega 0. Angular frequency. Okay, we generally call angular frequency as omega, so you can call this as omega 0. And these are the 3 dB frequencies, omega L, lower cutoff frequency, and omega H. So these are the 3 dB frequencies, and this contributes the bandwidth of the resonance curve. Now what is the value of omega H, omega L and omega H in correspondence or in relation with that of omega 0? The value of current, you can see the current is same in these 2 points, that is at omega L and omega H. The value of current is same. This is the current axis. And omega h is equal to omega L is equal to 1 by root 2 of omega 0. That is, it is 1 by root 2 times 1 by root 2 multiplied with the, sorry, this is the current. Okay, so you have to represent it as IH. IL is equal to I0. So if this current value, I'll write it here. If the current is I0 at the resonance and IL and IH at these two frequencies, that the 3 dB, these are the two 3 dB frequencies and this is the 3 dB bandwidth. So if omega L and omega H are the two 3 dB frequencies, the value of currents at that particular frequencies is equal to 1 by root 2 times the current at the resonant frequency. This is the relation. Please note this down. Okay, so the current at the two 3 dB frequencies is 1 by root 2 multiplied with the current at the resonance. The resonance current is the peak current or the maximum current. Okay. So the answer is, I'll read out the question once again. At 3 dB frequencies, current in the series RLC circuit equal to the current at resonance multiplied by 1 by root 2 is the answer. The options can be 1 by 2, 1 by 3, 1 likewise. Anyway, the answer is 1 by root 2. The next question is this. This is actually a question which we have already discussed in one of the previous year question discussion videos. Anyway, since it belongs to the series RLC circuit questions, I have included that in the video because it is one of the important questions. Okay. So if you have already seen this question, please you can skip this question and see the next question. Okay. The value of R, L and C in a series RLC circuit that resonates at 1.5 kHz and consumes 50 watt from a 50 volt AC source operating at the resonance frequency. The bandwidth of 0.7 kHz. So the question is to find the value of R, L and C of a series RLC circuit. So you need to find R, L and C. These three values we need to find. And we have been given some informations about the circuit. First thing is that we have been given the resonant frequency. A series RLC circuit resonates at 1.5 kHz means the resonant frequency in hertz is being given. That is F0 is 1.5 kHz. Also, it is being given that it consumes, that is this circuit consumes 50 watt, the power consumption from a 50 volt AC source. So the voltage V, or you can write or draw like this. This is a source. Okay. And it is having 50 volt. Okay. So there is a 50 volt. It is an AC source. Okay. So it consumes 50 volt from an AC source. The voltage is 50 volt. The power consumption is 50 watt. Okay. And also it is being given that the bandwidth is 0.7 kilohertz. Okay. Bandwidth is 0.7 kilohertz. Okay. So this much of information is being given. Now what all things we need to find? We need to find R, L and C. First, in order to find the value of R, you can use the relation power is equal to V square by R. Here, it is being given that the power consumption is 50 watt and the voltage of the source or the voltage applied is 50 volt. So, from that you can find R value, right? So, I am going to use a relation R is equal to V square by P. V is 50. So, 50 into 50 by 50 watt. So, the value of R obtained is 50 ohms is the resistance value obtained. So, for finding the resistance value, I have used this statement that it consumes 50 watt from a 50 volt AC source. So, from that relation, I have obtained the value of R. I'll draw the circuit here. R is equal to 50 ohm. Next, we need to find the value of inductor or inductance. Okay, so for finding the value of inductance, we can use the relation bandwidth is equal to R by 2 pi L. Okay, so here R value is now known to us from the first part. We have already solved that R is equal to 50 ohm. Bandwidth is 0.7 kilohertz. L we need to find. So from this relation of the bandwidth of a RLC circuit, bandwidth is equal to R by 2 pi L. You can substitute for bandwidth and resistance and you can find the value of inductance. Bandwidth here, okay, the value is 0.75. Earlier it was 0.7. I have corrected it. Please correct in your question also. Okay, so I'm going to substitute it as, okay, first I'm going to write in terms of L. L is equal to R by 2 pi into bandwidth. So, I'll write it above. L is equal to R by 2 pi bandwidth. R is 50 by 2 into pi into bandwidth is 0.75 into 10 raised to 3. So, this is the sum we need to solve to find the inductance value, and if you solve it, you will get it as 10.6 millihenry is the value of inductance obtained. That is, if you solve 50 by 2 pi into 0.75 into 10 raised to 3, you will get the value as 10.6 millihenry. Now you have the value for inductance also. Inductance is obtained as L is equal to 10.6 millihenry. Next, we need to solve for capacitance. For that, we will use the relation for resonant frequency in hertz. That is, F0 is equal to 1 by 2 pi into square root of LC. So, here the resonant frequency is known. L value is known. So, you can find the C value. So, for that, first I will square on both sides. So, F0 square is equal to 1 by 4 pi square LC. Right. Directly you can take or you can write for C. I'll write it above. C is equal to 1 by 4 pi square into L into F0 square. So this is the equation to find the value of capacitance. C is equal to, I'm going to substitute the value for L and F0 because L value is known to us now and F0 is already been given in the question. 4 into pi square into 10.6 millihenry. So it is 10.6 into 10 raised to minus 3. It is then into F0 square. So 1.5 kilohertz into 10 raised to 3 the whole square. If you solve it, you will get it as 1.06 microfarads is the value of capacitance obtained. So you'll get, I'll write it above, C is equal to 1.06 microfarads. So the value of R is obtained as 50 ohm, the value of L is obtained as 10.6 millihenry and C is obtained as 1.06 microfarad. So how to solve this question? The values given in the question is the voltage source value is given, power value is, power consumption of the circuit is being given, bandwidth is given and also the resonant frequency is given. So from the power consumption and voltage relation, we can find the value of R. And if you take the equation for bandwidth, that is bandwidth is equal to R by 2 pi L, you can find the value of inductance. Then by taking the equation for the resonant frequency, which is F0 is equal to 1 by 2 pi square root of LC, you can find the value of C. So this is how you need to solve this type of RLC problems. Okay. So I hope it is clear. The quality factor, the Q factor of a series RLC circuit increases with dash. The quality factor equation Q is equal to, we have already seen the equation in terms of the resonant frequency and bandwidth. In terms of the components, the components of series RLC circuit, you can write it as omega L by R is the value or is the equation for the quality factor of a series RLC circuit. So the quality factor increases with dash. A, resistance decreases. Yes, the correct answer is as the resistance decreases, quality factor increases. Then resistance increases, no, because R is in the denominator. So if R increases, Q has to decrease. So this is not the correct answer. Voltage increases, no. Voltage decreases, no. So the correct answer is when the resistance decreases, quality factor increases. Okay, so this is the equation for finding the quality factor in terms of L and R. Q is equal to omega L by R is the quality factor of a series RLC circuit. Next question. Impedance of a series RLC circuit is dash. That is the equation for finding the impedance of a series RLC circuit. Z is the impedance, and it is given by R square plus XL minus XC the whole square. Now at resonance, so this is the equation. Z is the impedance, R is the resistance, XL is the reactance of the inductance, XC is the reactance of the capacitance. So we know there is a resistance, there is an inductance, there is a capacitance. R, L and C. And the resistance or the impedance of these three components, if it is taken together, that is a total impedance of the RLC circuit, series RLC circuit. So R is purely resistive. So R square plus XL is the reactance of inductance, XC is the reactance of the capacitance. At resonance, what happens is that this XL will be equal to XC. Okay, so at resonance, XL is equal to XC and there will be only resistance, and square root of R square means it is R. That is the total impedance of a series RLC circuit at resonance is purely resistive. This is very important. This is a very important point you should know about the resonance and series RLC circuit. So at resonance, what happens is that XL will be equal to XC. So when XL is equal to XC, in that equation, XL minus XC will get cancelled and square root of R square is R. So the impedance of the total series RLC circuit at resonance is purely resistive. Is contributed by the resistance component. Okay, so this is another important thing you should know. Anyway, for this question, the answer is, the impedance equation is this. R square plus XL minus XC the whole square is the equation to find the impedance, total impedance of a series RLC circuit. Okay. Value of C which gives a critical damping in circuit is dash. So, this is a series RLC circuit and you need to find the value of capacitance which will cause critical damping in this circuit. So what is actually damping? Damping means the decay of oscillations of this circuit is called damping. So when you introduce the resistance component, it will cause the decay of oscillations, or damping is actually contributed by majorly by the resistive component. And the damping constant is defined as tau for a series RLC circuit. It's equal to the value tau, that is damping constant tau, is equal to alpha by omega 0 is a damping constant. Okay, where omega 0 is the frequency, resonant frequency, which is in angular frequency. Omega means it is an angular resonant frequency. Alpha is the attenuation caused by damping. Alpha is the attenuation caused by damping, and omega 0 is the angular resonant frequency. Now, based on the value of this damping constant tau, you can classify this system as critically damped, underdamped or overdamped. That is, just like we say the case of modulation, that is critically modulated, undermodulated or overmodulated based on the modulation index, we can say, right? So just like that, we can say based on this damping constant or damping factor, you can call it, if this tau value is equal to 1, we can say it is a critically damped system. For this question, it is a critically damped system, so the tau value is equal to 1. Then if tau value is greater than 1 means it is overdamped system. If tau is less than 1 means it is an underdamped series RLC system or circuit. Okay, so based on this damping constant, we can say whether it is critically damped, overdamped or underdamped. Now for this question, the value of tau is equal to 1. So you can write the attenuation due to damping is equal to angular frequency, angular resonant frequency, and the value of alpha is equal to R by 2L. And we know that the resonant frequency in angular values is equal to 1 by square root of LC. And you need to find what? You need to find for this question, you need to find the value of C, which will cause critical damping in this system. We have to consider that this system is critically damped and we need to find the value of C. So we'll take squares on both sides. R square, I'm going to write it here. R square by 4L square is equal to 1 by LC. So you can remove this and you can write C is equal to 4L by R square. Right. Now you need to substitute C is equal to 4L by R square. And you need to substitute the values here. R is 1 ohm, L is equal to 2 Henry. I'm going to substitute and find C is equal to 4 into 2 by R is 1. So 1 square. So you can find, or you will get the value of C is 4 into 2 by 1 is 8 farads. The value of C obtained is 8 farads is the value of this capacitance obtained when the system is critically damped. The Q factor of a series RLC circuit is 5 and resonant frequency is 1 kHz. Bandwidth is dash. This is again the simple relation for quality factor. Q is equal to F0 by bandwidth. So what all things are being given? Q is 5. F0 is 1 kHz. So you can directly find bandwidth is equal to 1 kHz by 5. 1 kilo means 1 into 10 raised to 3. So the value obtained is 1000 by 5 or 200 will be the value of bandwidth. 200 Hertz it is. Okay. So the value of bandwidth obtained is 200 Hertz. So these type of quality factor related or bandwidth, that is questions which is asking bandwidth or quality factor or resonant frequency, these type of questions, there can be a lot of questions you can expect in these competitive examination because the series RLC circuit and resonance is one of the very favorite topics for all the exam panels. So I really hope that these questions were useful for your preparation if you are preparing for any competitive examination, not just SAC or technical assistant or ISRO, any competitive examinations. This topic is very important. So I really hope that this video is useful. If yes, please don't forget to give a thumbs up and also share these videos with maximum of friends. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.